This video updates an earlier version and includes changes which supersede the former seminar presentation.
Let's talk about grounding. Specifically, let's talk about temporary grounding for personnel protection. This has been something of a controversial issue throughout the electrical industry over the past few years. It seems that a lot of the controversy and the disputation has swirled around this issue of single point versus dual point grounding. I hope that by the time you've seen this presentation, you'll come to realize that that never was the issue. The term single point grounding was designed to be applied to a specific grounding technique. And it may be an unfortunate misnomer. I say unfortunate because the use of the word single introduces into the issue numbers, where numbers really don't need to be. There's a term that I like much better, and that term is equipotential grounding. Equipotential is a contraction of two words, equalized potential. And the creating of a zone of equalized potential is the single most critical element to be considered in any grounding program. When a power line is de-energized and temporary grounding is applied, you have certain objectives in mind. One of those objectives is to reduce the electrical potential of that line down to zero and hold it there as much as possible. The second objective is to create an exit avenue for any induced voltages or stray voltages that may be induced along the line. And you want to have a program in place that will, in the unfortunate and unlikely contingency that the line should become accidentally re-energized, that line will be returned to an open condition as rapidly as possible. Now, those are the things you're trying to accomplish. And that's what you're trying to prevent. Now, I'm going to show you a series of pictures now of an actual accident. It occurred in Jacksonville, Florida in 1967. A lineman working up a pole made contact with an energized conductor. By the time the other crew members found him, he was hanging upside down in his belt, he was unconscious, and he was not breathing. It happened that a newspaper photographer was present at the scene of the accident, and he got a series of pictures, for which in 1968 he won the Pulitzer Prize for photography on the strength of this photograph. Now, I'm sure you recognize immediately that that's an outdated rescue technique. Dominant thinking in the industry, and has been for years, is to bring the man to the ground as rapidly as possible and then begin your resuscitation program. But in 1967, this was a very current thing to do. And it worked. He regained consciousness before he reached the ground. He was able to assist in his own rescue. Now they have him down on the ground. They're giving him oxygen. Look down at his right foot. You can clearly see the exit wound. This is where the current left his body. Now, this is a situation where a man made contact with an energized conductor. This will inevitably be the consequence of something like that. We can say, and we would be right, had he been working on a de-energized and properly grounded conductor, that this accident could not have occurred. Now let me suggest a frightening possibility to you. That if in fact he had been working on a de-energized and grounded conductor, a conductor grounded using equipment and using techniques very commonly in use throughout the industry today, that under those circumstances there is a very real possibility that an accident like this one could occur. Contrary to popular opinion, that is not a photograph of our department head reviewing my expense reports. That's a test subject being subjected to an electric current. A few decades back, a tremendous amount of research was undertaken on the subject of the effects of electricity on the human body, and they actually found volunteers willing to do this. Some of the things they were looking for were perception current, the smallest current that the body can detect. At what level of current flow can you begin to feel? Reaction current, a current flow large enough to cause an involuntary reaction. By involuntary reaction, we mean simply loss of voluntary muscle control. And of course, let-go current, the maximum current a person can tolerate and still release the conductor. How much current can you stand and still retain voluntary muscle control? Now, there were any number of these projects undertaken, and they all arrived at essentially the same results. If the results varied, they varied by a few milliamperes here or there. I have a chart that I'm going to show you. It's entitled Quantitative Effects of Electric Current on Man. The chart is in milliamperes. And for our discussion here today, we will restrict ourselves to the categories of alternating current, 60 cycle, and min. Now look over to the left-hand column, number 1. Slight sensation on the hand. This is where you may begin to feel it. And look at the value. 0.4 milliamperes. Or in other words, slightly less than slightly less than half of 1/1000th of an amp. Look at category number 2, perception threshold. This is where you're absolutely clear. This is where you're certain that you're feeling electric current. And the value is 1.1 milliamps, or in other words, slightly over 1/1000th of an amp. Come down to category number 5, painful shock, let go threshold. This is the maximum amount of current that you'll be able to tolerate and still retain voluntary muscle control. And the value we're looking at is 16 milliamps. Now come down to the frightening one, category number 7, possible ventricular fibrillation effect. What the chart is telling us here is that with values as low as we see illustrated on the chart, these values were in some test cases enough to throw a heart into ventricular fibrillation. And you know what that is. That's where your heart leaves its normal beating pattern. It goes into a vibrating mode just prior to shutting off. There's no recorded instance of a heart going into fibrillation and ever recovering unassisted. If you get into that situation, you've got to have help, and you've got to have it fast. Now look at category A. 0.03 second shocks. That's 3/100ths of a second. At 60 cycles, approximately 1.8 cycles will lapse in that amount of time. Let's round that off to 2 cycles. And we're saying that for 2 cycles, 1,000 milliamps, or in other words, 1 amp, was in some test cases enough to throw a heart into fibrillation. Category B, 3-second shocks. Now 3 seconds is not a long time either, unless you're being subjected to an electric current. And for 3 seconds, we're looking at 100 milliamps, or in other words, 1/10 of an amp. The value traditionally considered to be lethal dosage. Now my object in showing you this is to illustrate that it takes an incredibly small amount of current to do catastrophic harm. You cannot afford to expose yourself to very much current for very long. And you need to be absolutely certain that your grounding program is protecting you against this possibility. We say that we ground a line to provide safety of the worker from induced voltage from adjacent lines, electromagnetic feedover from adjacent lines or systems on the same structure, a storm on another portion of the system which could give rise to a transient, that's a high-priced way of saying a lightning strike, or the ultimate contingency, the accidental energizing of a system following a standard operating procedure, or in other words, a human error. We'd like to believe that we've achieved a state of art in the industry today where this cannot and does not occur. The record clearly shows otherwise. It occurs with alarming regularity. And it has to be the chief consideration in your grounding program. You have to be sure that your grounding program will protect you from an accidental re-energizing of your system. We contend that the key to safe grounding and jumpering then is to keep the voltage drop across the lineman to a minimum. A few moments ago we looked at a chart that gave us some incredibly small values of current that could produce catastrophic harm. But before any current will flow, there has to be a voltage drop. If we can eliminate that voltage drop, we can eliminate that current flow. Now I'm playing pretty fast and loose with that term eliminate there. What I mean by that is if we can keep that voltage drop down below the threshold of danger, we will likewise keep the current flow down below the threshold of danger. Now let's look at the way grounding has evolved over the years. There was a point in time when it was not unusual to see a grounding configuration like this. We have 3 phases being grounded by 3 long leads coming down to 3 individual driven grounds. The problems are obvious. The leads are long and heavy and cumbersome, and you have the problem of the earth resistance between the 3 driven grounds. Some improvement was made on this by eliminating 2 of the driven grounds and bringing all 3 leads down to 1 driven ground. But you still have the problem of the long down leads. Considerable improvement was achieved by this technique, jumpering all 3 phases together and then bringing 1 lead down to a driven ground. Repeatedly, tests have proven that jumpering 3 phases together will give you your best, your fastest breaker time in the event of an accidental reclosing of that breaker. That's putting a dead short on your system. Your breaker will see that sooner than anything else and react to it. And of course, with the down lead to a driven ground, you have your exit avenue for induced voltage. But all of these techniques overlook some fundamental aspects of electricity. Electricity is essentially amoral and totally indiscriminate. And by that I mean simply it'll go anywhere there's a path for it to go. It'll harm anyone who gets in its way. Put an imaginary lineman on that structure, standing near that center phase, with his feet on the structure and his hands in contact with the center phase. What does he represent at that point? Very obviously, he represents an alternate path to ground. Think back to your basic fundamentals of electricity, parallel circuitry, resistors in parallel. What's the voltage characteristic of resistors in parallel? The voltage drop across each resistor is the same. A man in that situation represents a resistor in parallel. He is an alternate path to ground. If that circuit were to be accidentally re-energized, there would be a voltage drop across that man and a resulting current flow. Now this slide, in its simplest possible form, illustrates the concept of equipotential grounding. Consider what we have here. All 3 phases are jumpered together. This gives us our best breaker time. In this case, we're jumpering from the center phase down to the structure, and we are bonding the lead to the structure just below the work area. Now consider what we have there. From this point of attachment upward, where this lead bonds to the structure upward, everything in that work area, every part of that lineman's body, and everything that he could possibly reach or touch is at the same electrical potential. Before you can have a voltage drop, you have to have a difference in potential. If we can effectively eliminate that difference in potential, we can eliminate the voltage drop, we can eliminate the current flow. We have achieved a zone of equalized potential, wherein everything that that lineman can reach and touch is at the same electrical potential. This is the essence of equipotential grounding. I approach the issue of single-point grounding versus dual-point grounding not from the standpoint that one is superior to the other, but purely in the interest of illustrating some application techniques. This slide is entitled Jumpering Method of Two-Point Grounding on a Y-Connected System. The important thing to consider here is the sentence at the bottom of the slide. It says installed at each end of the work area outside the work area. The point being made there is that this is not the structure you're going to work. We have all 3 phases jumpered together, and from A phase we are jumpered down to the neutral. But very obviously we have not created a zone of equalized potential. Jumpering method of two-point grounding on a delta-connected system. On a delta system, there is no neutral present on the pole. Therefore, we must rely on a driven ground and a lead from one phase down to and securely connected to that driven ground. This slide is entitled Jumpering Method of Single-Point Grounding on a Y-Connected System. Note the sentence at the bottom of the slide. It says installed at the work site. Consider what we have here. All three phases are jumpered together. From A phase, we are jumpered down to the neutral, and from the neutral, we jumper down to a grounding cluster securely mounted on the pole well below the work area. From the point of attachment of that grounding cluster upward, everything on that pole is at the same electrical potential. Let me show you an example of a grounding cluster. It consists of a metal bar that attaches to the pole of the structure by means of a chain attached to a wheel binder. It simply clamps around the pole and provides metal contact all around the circumference of the pole. And of course, the metal bar provides a point of attachment for your grounding clamps. The ideal location for your grounding cluster is just below the work area, just below the lineman's feet, where it will not represent an obstruction for the lineman working on the pole. Now let's look at a few more slides. This slide is entitled Jumpering Method of Single Point Grounding on a Y-Connected System with an Undersized Neutral. Now what we mean by an undersized neutral is a neutral conductor that may not be equal to the available fault current. By definition, fault current is the maximum amount of current that a source can deliver to a site. The source in most cases will be a substation. How much current can that substation deliver to the point where the work is being done? Now, by virtue of the fact that you install a ground on the line, you ensure that in the event of an accidental re-energizing of that circuit, a fault current will flow, because your source or your substation looks down the line when the breaker closes, sees virtually no resistance, and it just dumps everything it has out there. If your neutral conductor is not large enough to handle that value of current, you can augment that neutral by use of a driven ground and a lead from your grounding cluster down to the driven ground. And this says jumpering method of single point grounding on a delta connected system. And of course you can see we're jumpered phase to phase. From A phase we jumper down to the grounding cluster, and from the grounding cluster down to a driven ground. From the point of attachment of that grounding cluster upward, everything in that area is in a zone of equalized potential. Now this is a technique well worth considering. It says two-point equipotential grounding system on a Y-connected system. The sentence at the bottom of the slide says installed at each end of the work area. Inside a work area may also be used for single-point grounding. Now you'll notice something here a little different than you saw before. Note, of course, that we're jumpered phase to phase. And then from A phase, we jumper directly down to the grounding cluster, and from the grounding cluster back up to the neutral. The advantage of this is that it leaves us with only one ground clamp attached to the neutral conductor. As an example, if you had a fairly small neutral conductor, perhaps a high value fault current for a long duration, what can happen if you have two ground clamps on that neutral? The conductor between those two clamps can act like a fuse. And of course the object of a fuse is to blow. And this can happen. Now to compound all your other problems, you've got a neutral on the ground. It's a good idea to minimize the number of ground clamps that you have on your neutral in an effort to avoid this situation. Now think back to the first slide that I showed you. And it said at the bottom of the slide, installed at each end of the work area, outside of the work area. Now, with the structure that we have on this slide, immediately one span to the left is a securely grounded pole. Immediately one span to the right is a securely grounded pole. At the work area, at this structure, all we need to achieve our zone of equalized potential is a grounding cluster attached to the pole and one lead from that cluster up to the phase. And of course, two-point equipotential grounding system on a delta-connected system. This is simply a delta system in the same situation. We have Immediately to the left, a grounded pole. Immediately to the right, a grounded pole. At the structure we're going to work, we need only apply a grounding cluster and a lead up to the phase. Even on a Y-connected system, you can jumper from the cluster to the phase. We say that we have a person on the structure and we have a person on the earth, and we ask, can we protect them both? Now, what are we talking about here? Very obviously, we're talking about step potential. Step potential is caused by a flow of fault current through the earth. This current creates a voltage drop at the earth's surface. You have a point of entry for a fault current into the earth. From that point of entry, a voltage gradient will radiate outward. A man standing in that voltage gradient will realize a potential difference between his feet. A potential difference which will allow a voltage drop, which will produce a current flow. You have a potentially life-threatening situation. This chart basically illustrates the situation. Here we have a structure, a fault current coming down that structure. The jagged line at the bottom of the slide represents the fault current, the voltage gradient radiating outward. You can see the man standing in that gradient. If you look up in the upper right-hand corner of the slide, you see an equivalency chart. Recognizing from this that in this situation there would very definitely be a voltage drop across that man, producing a current flow. Now, nothing would please me more than to tell you that there's a simple and easy way to deal with this problem, and quite frankly, there isn't. About the best recommendation that can be made is the use of a localized mat at the base of the structure. It can either be a grounded mat or an insulating mat. Either one will create a situation at the base of that structure wherein there is no difference in potential between the man's feet. Now, you can see obviously what you've done here. You've moved the danger point outward from the base of the structure out to the edge of your mat. And you need to be aware of that problem. Touch potential is just another expression of the same problem. A man standing on the earth in contact with the structure represents an alternate path to ground. In the event that a fault current were to flow down that structure, there would be a voltage drop across that man, there would be a current flow through him. It essentially has to be dealt with the same way.